Okay, good morning to you. And that was the Cranberries' Dreams. Now, if you've been working and with the intensity I would like, you had dreams about statistics. If not, then we haven't quite reached the level I'd like. We're looking at homework in Chapter 2. I returned Chapter 1 homework. Let me just give you some feedback about Chapter 1. The three things I wanted to look at in particular in Chapter 1 would be the histogram, the stem plot, and the time plot. And the two problems that were most appropriate to that happened to be at the end. And they are two problems we had discussed. So I thought that gave you the best shot at getting them done, having heard discussions regarding both problems. And unfortunately, in some cases, several of you did not get that far. And I graded 3 points per problem. And if you did not complete the assignment, I took another point off. The sixth problem at the beginning I thought was an appropriate place to start. And I had asked you to follow the guidelines for the number of intervals, the boundaries, that you have a frequency table, that you use a straight edge, and so on. So that's the list of 3 problems I graded. And in the back-to-back stem plot, we had talked about that. The important thing there was to try to go ahead and round off values before you started. You needed a legend. And you have to make sure you answer the questions, such as, were there suspicious points? And address the issues that are asked. In the lab, just a reminder there that the third part of the lab, in terms of the intro, is intended that you cover that rather thoroughly. And 2 sentences just don't quite do it to provide the overview of what's covered in the introduction. There were 10 points on the lab. I had mentioned to you that you should have the page more or less filled up. That means you had to go to page setup or print setup and change margin setups and such. We had talked about that in class. And I expected again to have color as an output for your pie charts and your bar chart. And just a comment on the pie chart, if your colors are difficult to distinguish, and some of you had them very, very close in color, that's something I was sensitive to and took off a half point if I could not, from your legend, distinguish what country or continent, I should say, was which based on what I was looking at. The scores went from 10 down to around the 3, 2.5 range, and would encourage you to check with me if you have some concerns about what you're expected to have in the labs. Drop by the office. The office hours are from 1 to 2:30, Monday through Thursday. I encourage you to drop by or phone if you need to ask questions. The lab that we do this week is going to be number 3 on histograms. And essentially what we're going to do is focus on the population of birth rates globally. And we're going to ask a very fundamental question. Is that distribution bell-shaped? And we're going to see what happens if you don't have enough intervals and what happens if you have too many intervals. Now the key to that, and I suggest you make a note of this, and then after making a note of it, maybe reference that note when you go back and do the lab. It appears that you are not referencing notes when you go back and do some of your work. What you're going to find if you have not enough intervals is that you lose information. So if you don't have enough, you lose information. If you have too many, you generate noise. And that'll become more evident, I think, as we look at the lab tomorrow. So again, not enough intervals, you lose information. Too many intervals, you generate noise. In essence, overload on information. And what do you use to determine just right? Powers of 2. Y equals 2 to the x. So if we have 200 and some data values, what power of 2 is appropriate? If nothing else, have your calculator out or sit there and do the powers of 2 to determine what it should be. So you can just sit there and multiply by 2 and keep track of how many times you're doing it. And as Sean said, it is 2 to the 8th power. So you're going to want about 8 intervals. So we'll start that lab with 3 intervals, and then I think I'll kick you up to about 20 with the idea of a scenario that is not unlike Goldilocks and the 3 Bears. This porridge is too cold, this porridge is too hot, and this porridge is just right. That's the contrast we're going to make, and I don't expect to read about Goldilocks as part of your output in the lab. Okay, so that'll be tomorrow. And just a comment beyond that, there is a problem I expect you to take quite seriously, and it is a problem in which you try to explain to somebody else. It's part of the discussion questions. You try to explain to somebody else how to find the lowest boundary and the highest boundary, okay, and how to find the width of the intervals. And you're going to write that out so somebody else would be able to read it and understand. Okay? Not unlike what you would do in the short answer questions, part 1 of the exam that we've talked about, where you are to explain in paragraph form what the answer should be to the question I have asked. And just a reminder, I expect complete sentences. Complete sentences include a subject, a predicate, okay, and not just a number. So if you did not use complete sentences in answering the questions in the discussion questions, then I was critical of that. So I think that covers the grading. And I asked before we started the presentation this morning if there were questions in Chapter 2. And I have 4 questions that have been asked. And the questions we're going to look at this morning, minimally, will be 8 and 9, 12 and 40. Those were the questions that were addressed in answering my query about what would you like to cover. So let's take time to look at Chapter 2. And I need to find I went 1 page too far. I would like the 8th question. It's on page 47. Okay, there's a stem plot referenced. The stem plot that's referenced is page 25. And it displays the distribution of the percents of residents age 65 and older in the 50 states. It tells you that stem plots help you find the 5-number summary because they arrange the observations in increasing order. Now, when you do a stem plot with a computer program, and that's typically where they are done, such as stat graphics, you find that this caveat that the leaves are in a chronology or in chronological order is done. When you do a stem plot by hand, I have not asked you to go ahead and rearrange the leaves so that they are in order. So you have to be careful that what's being asked in this problem, that is to find the 5-number summary, is something that you wouldn't necessarily practice longhand because we have not made the request that you order the leaves. The second comment relative to this problem is that if your data has been rounded, and that is often the case in order to create the stem plot, then if you find the first and third quartile and the median from the stem plot, you will not have the correct values. Okay, so if you're going to do the 5-number summary from the stem plot and you have rounded first, these are only approximations. You would be expected to go back to your original data and find what number is associated with the rounded value you gave. It's rather interesting when you look at stat graphics and you look at the stem plots. Oftentimes they are rounded, as we have mentioned, and then when they list low values or high values, translate that into suspicious or extreme points, they will give those data values precisely, even though the values in the stem plot have been rounded. So in this case, you were to give the 5-number summary, and then you were asked to do what David Moore here capitulates to. And I say that with some humor. He has avoided looking at the complete box plot. Now, the complete box plot involves the fences we did in class, where you go ahead and you look at the IQR. You take 1.5 times the IQR, 3 times the IQR, and you add that to Q3 and you subtract it from Q1, both of those products. That gives you upper and lower fences. And we have said that anything past 1.5 IQR added to the higher fence or subtracted, higher, didn't say quartile, and I meant to say higher quartile or third quartile. Let me write that as we go to the board, Jennifer. So anything beyond Q3 plus 1.5 times the IQR will be at least what? Suspicious. Now, it could be extreme, because this just defines the upper inner fence. So we have this as the upper inner fence. Then you have an upper outer fence, which is Q3 plus 3 times the IQR. Now, all David Moore is doing at the moment is asking, have you met this one criterion? Are you beyond 1.5 IQR of Q3? If so, then we have a point we challenge. I wish he would take the extra step. Maybe in the next edition. It's taken 4 editions for him to include this problem finally and address the fences. As I look at the data, and by the way, Florida and Alaska are the two states that are being questioned about whether or not they are suspected outliers. And so as we go back to page 25, and I look at 19, okay, these are to be percents, and by the way, it's difficult from page 25 to determine which state is supposed to be Florida and which is to be Alaska. You have to turn the page. For 26, it says there are 2 outliers, and it says Alaska has the lowest percent and Florida the higher. Any idea why that's the case?
Still people like Florida is more respectful like Alaska.
Yeah. Okay, we talk about snowbirds. If you live in Minnesota and you've had it with the long winter that seems to go forever, and you have money, you migrate with the rest of the birds and go south. Alaska is probably where a younger person would like to be, who doesn't mind the cold weather, more invigorated by it. And so geographically, I guess, in terms of climate, is why these values might be what they are. But if you'll look at the stem plot, and this is something I want to bring to your attention, because some of you in stem plots are inclined to eliminate certain stems just because you don't have data for them. So as I bring this down, okay, just a moment, things are going to have to be adjusted accordingly. Okay, if you'll look at the stem plot as we go to the document cam, it's this space between the 5-7 and the 8-5, which suggests that the 5-7 is too far from the rest of the distribution to be a what? A data point that is consistent with the rest of the distribution. Now this bothers me right here because this little part from 8.5 to 106, and this must not, this can't be 106%, so I'm going to have to assume without a legend, and that's the sloppy part of this graph, you have to interpret that that's a 5.7%, this is an 8.5%, but this looks like a little bell here to the left, correct? And then another bell here, and we say that that kind of distribution is what? Bimodal. So the mode is that data value that you have most often. The modal class is the class or interval that has the greatest amount of data. So we have a modal interval or modal class at about 9 and another one that appears to be about 13. Okay, so 5.7% doesn't fit either of these two distributions very well. Again, a Sesame Street criterion. It's not like the others. This is not as much separation here at the 17.6, okay, but not as bad. Okay, so to that extent, if I have one more value at 16, I would not consider that unusual whatsoever. These are suspicious points, and one way of dealing with them is to eliminate them in what we call a trimmed data set, where you take the lowest and the highest and toss them out. Furthermore, if you have two separate distributions, you might want to isolate on them separately. So to that extent, as I come back to the document cam, I might want to isolate these 5 states and get some idea what's involved there, and then isolate on these. Now, as I look at this, the low and the high are, I hope, pretty much a piece of cake for you. Very clear what they are. Now, the question, how do you generate, then, the first quartile? So as I go back to this, I need to know how many pieces of data I have. And I believe these are going to be all the states, 50 states. So where is the median and the quartile going to be located? Or where are the median and the quartile going to be placed? Let's look at the median for just a moment. The median, as I go to the board, is going to be what position? Okay, it's in the middle of the data set, 25 below, 25 above. So we say the position, not the median, but the position is going to be equal to n plus 1 over 2. So I do need the 25th and 26th data value. Now, it's important to find the median because the quartile is going to involve all the data points either above or below the median. So since I have 50 states involved, I know where the position is going to be. I don't have the value here. And for the 5-number summary, okay, I'm going to need that. So let's do a count. And as we come back to the document cam, start here at 1, 2, 3, 4, 5, 6. Then there's 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. It looks to be between 12.7 and 12.8. Is that correct? So I'd have 12.7 plus 12.8 divided by 2. Do we concur in that? Okay, I see a few heads bobbing up and down. So the median turns out not to be a data value. It's going to be at 12.75. Now, I look at the 25 values below the median, okay, and I want to go up to the 13th value for Q1. So the location of Q1 will be at the 13th data value. This particular stem plot starts from low going to high. The advantage of that is that you can rotate it. So if I have my stem plot and I rotate it counterclockwise, my stem plot is going to look like a histogram. That's the argument. So as I come back to the stem plot, I want the 13th data value. So remember that was 1, then we have 2, then we're at 5, 6, 8, 10, 12. 13 is 11.7. So Q1, I believe, is at 11.7%. Do we concur? And then Q3, I could start from the upper end, and that work back 13 values. So as I come back to the stem plot, 1, there's 3, 5, 7, 9. Now I've got to come back to here. 10, 11, 12, 13. It looks like 13.5. Do we concur with that? Now I do need the low value and the high value. The low value, I believe, was that 5.7, which is considered a outlier potentially, and then the high value is at 17.6. Now technically these are all percents. I'm just writing them this way. And I think you can appreciate what you're missing by looking at the legend. That's not there. Okay? And I would be critical without a title. You have to read the problem and figure out what's going on, and it would be much better with the title on it. Now we still need to have Q3 plus 1.5 IQR. So I need the IQR. The IQR is going to be Q3 minus Q1, and that's going to be 13.5 minus a value of 11.7, and so that's going to come out at 1.8. So if I take 1.8 times 1.5, we're at 2.7. Do we agree? And so if I look at the upper inner fence, which is what I'm interested in, relative to that very high value, okay, I'm going to have Q3 plus 1.5 IQR, just restating that, and Q3, okay, don't go too far on me, Jennifer, because I need to pick up the Q3, which is at 13.5, and I'm adding to that the 1.8, and that's going to give me 15.3. And if I'm at 15.3, let's go back to the document cam. That's why the question that is being raised, are there other values? If I've done my arithmetic here, it would appear 15.6 is also what? A suspicious point. So it looks like I have suspicious points at 15.6 and 17.6. So the question, have I done my arithmetic right? Yes, Sean.
When you have the IQR, what 1.8 times 1.5? Aren't you just leaving it as 1.8 when you go down 2 rows?
I did, unfortunately. What Sean asked, when I did this at 2.7, I didn't adjust here for 2.7. So my conclusion may not be the same. And so at this point, boy, that managed to make more of a mess than it did clean it. So instead, I'm at what? 17.2? 16.2. And so if that's the case, I have what? Just a 17.6. Thank you for the correction. So at this point, I now need to look at what? Q1 minus 1.5 IQR. And that should establish the other value. Do we need to go any further? Does that answer the question, whoever asked for the problem? Okay? Anybody else in this problem as far as questions? Is that enough? Not done. I still would need to go a bit further. What I would expect of you is that you would practice the box plots that you have in homework to go beyond what was asked here, that you actually find all these fences. And just as a practice, even though it was not asked in this problem, I would be inclined to draw a box plot for this problem in preparation for the test so you know how to identify the fences, the length of the stem, I should say leaf, stem, leaf, what do I want? Whisker there. So let's look briefly what I'm talking about in process. If I have, okay, I'm just going to make a generic box for the moment. So this is for the box plot. And I'm going to, these are called hinges, by the way, and I'm going to have a median line in there. This is the general nature of a box plot. Now the question, how long does this whisker go? How far does it go? If I have a suspicious point. Well, the suspicious point I have, and at the moment I don't know whether it is extreme, that's the 17.6. So if I think of 3 times the IQR, which is a 5.4 added on to here, that would be at 18.9, so it's not extreme. So I'm going to have a suspicious point out here, which is going to be where that 17.6 is. How far does this whisker then go? I go back to the document cam, and my next value is that 15.6. So this is only going to go to 15.6. So if I think of what I would have down here in a scale, this is going to be the, I need to look at what I'm doing there, 15.6, I believe. So that's where that's going to terminate, not at the fence, which is 16.2. That's what you need to understand. So one more time. the whisker only goes to a point, the last point, or as Sean said, the second highest point, only to a point that's smaller than the upper inner fence. The whisker does not go to the fence. You do not see the fence in your box plot. Okay. Now I still need a mean marker in here, and we don't have the mean for all this, so I can't show you where that mean marker is. And again, on the left side, assuming that that 5.7 is a suspicious point, then let's see if that makes sense. If I have Q1 at 11.7 and I take 2.7 off of that, so I would be thinking of a lower inner fence of 11.7 minus 2.7, and that's at 9. The lower outer fence is going to be that 11.7 minus the 5.4, and that's going to be down at 6.3. And so it appears that what? That 5.7 is a what? An extreme point, because it is below the lower outer fence. So down here, I'm going to have an asterisk, and what I showed you on the computer actually involved a box with a plus sign for stat graphics. So where does the whisker go? This is at 5.7. My next data point is at 8.5. Somewhere up in here, we'd have to have a uniform scale below to show this. But that is as far as that whisker goes.
No, 8.5 is considered suspect. Why would that be a box as well?
If what now?
8.5 would be considered a suspect point.
Okay, at this point, I didn't check to see if I had another one. And if 8, the next one, I just went for the 5.7. Okay, at 8.5, it is between these two, so that would be what? You are correct. That would be a box at that point. And then what's our next point? 9.6. So up here at maybe 9.6, and my scale is certainly not uniform, this would be the whisker only going to 9.6. So this is a problem which would probably be very much worth your time to go ahead and actually, in a formal way, draw a box plot. To get the mean marker, you would have to go ahead and add all 50 data values, and that might be tedious. But the question, what skewing do you expect here? Now, in general, we've used the location of the mean and the median to distinguish or establish skewing. If the mean is to the right of the median line, we argue skewed to the right. Now, with this extreme point down here, I'm inclined to argue what? Skewing to the left. And so I would not be surprised at all if my plus sign were to the left of the median line. Now, I make a comment earlier, made one, that the longer whisker tends to be on the skewed side. But you have to be careful, because in the complete box plot, the whisker does not go where? All the way to the end. So this is a truncated whisker, even though if you carried it out in the simple version to the extreme point, it would suggest perhaps that you have skewing to the left. That would be the kind of analysis I'm going to expect on the exam. So you have to be cautious that when you do your homework, you anticipate the type of question and the thoroughness that I want on the exam. So a simple box plot done in the text without the fences, without the clarification of extreme and suspicious points, okay, would not give you full credit on an exam. Any question beyond that? So this problem is very rich in what it provides for us as an experience in preparing for the exam on a box plot. So in preparation, you might make a note for yourself, and again, refer to the note at some point in the future. do this problem in its entirety with a box plot to generate preparation for the first exam. Okay, that was the first problem. So let me come back center. The next problem is very close to that one. It's number 9. So let me move the camera for a moment. I need to go all the way back to page 50. And we have blood phosphates. We have a total of 2, 4, 6 data values. Okay, and these were made on 6 consecutive visits to a clinic. Now these phosphate levels, I believe, are associated with liver, but I'm not 100% sure of that. At any rate, the point being, with 6 data values, do you find very much information you can get? Well, the answer is going to be very limited. And could you establish normality, bell-shaped curve with only 5, 6 data values? And the answer is not very easily. But we would possibly be able to do a stem plot to see if we have any kind of pattern. If you're going to find the mean and the standard deviation step by step, you would like to establish before you do so that this data comes from a normal distribution. Otherwise, what would be your more appropriate analysis? The 5-number summary. Now, as you look at those data values, and can you picture having a stem plot with a 4, 5, and 6? If you do, you have 2 values at the 4, 3 values at the 5, and 1 value at the 6. Agreed? Can you visualize that stem plot that easily? Which would suggest maybe some normality. To get the mean step by step, formula, substitution, and answer. Is there any need to go further than that on that particular part A? And I'm not sure which part the question's on. So somebody who clarify, please, who asked for number 9. What is your question, or what did you want? Somebody asked for 9. Who was it? Nobody's going...
I didn't ask for it, but on the solution book, it shows something different.
Well, let me take a look to see what we're doing.
That says a 5 there, and then I go, well, that's not right.
Well, with 6 data values, you certainly wouldn't have a 5 in the denominator. So, okay. So if you're referring to the student study, or the study guide that the author's done, just to comment, the 9th problem has an error in it. Okay, which is not going to make you feel any better. Where do you use n-1? In the standard deviation, but not in the mean. If I look at the formulas, and the formulas involved for the mean, the summation of x over n, correct? That's where you provide your substitution. And what David Moore is showing, or at least the person who did the solution part for that problem, is showing you is actually writing down the 6 values and dividing by what should be 6. But in terms of what I'm asking you for clarification here, all you would have to do is enter the 6 data values. You provide for me the sum. You have a 6 here, and then you provide the answer. Now, my comment about n-1 has to do with the formula that you would be expected to use here. This is the conceptual formula for the standard deviation. So it involves a square root, a summation. You have each value of x in which you subtract the mean that you just calculated. So you get each deviation from the mean, square that deviation, add them all up, and in the denominator you have n-1, which will be a 5 in this case. Now that is the formula that David Moore is giving in the text and would be expected. However, I used an alternative to that, which allows you to document it a little bit faster. I think from the standpoint of the text and understanding what standard deviation means, it's probably worthwhile to carry out those 6 differences, square the 6 differences, add them up, divide by 5, and take the square root. I think that's a good exercise in understanding conceptually what's there. But you do have an alternative. And the alternative is the computational format, in which I take again the square root, But the quantity in here is n times the summation of the x squareds. Then subtract off the summation of x, which you have up here. You square that value before you subtract. And in this case, you have n times n minus 1, which is going to be a 6 times a 5. And there, you can just go ahead and take your values from the calculator using the summations. Now, do we need to go further than that? We're okay? And again, I don't know who asked for 9, but if there's any further discussion here, I'll be happy to entertain it.
So you're just saying you can use either or for standard deviation?
Yes.
Computational?
Yes.
Okay.
But as I say, again, the question was, can you use either one or the other? And the answer is yes. Which one gives you a better conceptual sense at the moment? And for the problem intended and what you'd be checking in an answer, that would be the preferred formula, but not an obligation to do that one for your homework. Relative to sort of eyeballing what your answer should be. What can you use to get an intuitive sense to know whether you have a reasonable value? We called it the poor man's standard deviation. And we said that this should be approximately equal to the range over the square root of the sample size. So if I think in terms of the range, if I go back to my data set, I have, and unfortunately that is not flattened out quite the way I'd like, but if we look at that, what is your range? 6, 4 minus 4, 6, is that right? So that would be at a 1, 8. So if I flatten and let that drop, this is going to be approximately, and I should use just an approximately here, 1.8 over the square root of 6. Now the square root of 6, okay, that's about 2.5, just about 2.4, between 2.4 and 2.5. So if I take 2.4 or 2.5 and put it into 1.8, what do I get there? Sean, I just saw you doing that. What did you get?
0.734.
734. Now, what did we get for the actual value when you did the problem? For S, what was it? 0.642? Okay, so this comes out at 0.642. So was our estimate reasonable? Well, it's off by a tenth. So I have 6.4 actually and a 0.74 doing it as my estimate. And all it is making sure that you did is the following. Before you took the square root, what did you have? In order to get this 0.64. So you've gone through all this. You take the square root and you get 0.64. Your S squared would have been something up around a 0.4, right? And if you see that 0.4 and you know that you should have something around 0.7, it may trigger a red flag for you to say, maybe I forgot to take the square root. Now, it doesn't work so well in decimals, smaller than 1, because your sense of a square and a square root relationship is probably not very well developed because you don't do it very often. That is, if you take this 0.64 and square it, okay, you're going to have something that's going to be a 0.4 nearly. It gets smaller. So when you square a decimal less than 1, you actually get a smaller number. So the magnitude is not quite as, not quite as impressive as if this were a 6.4 and you saw it as a 36. 36 now is larger than 6, and the magnitude seems much greater to you. So at any rate, any further question on that problem? That was number 9. Yes?
So would you expect us to find, like if you give us a problem with this, would you want us to put the four-minute standard deviation?
Okay, the question is, if I gave you a problem on an exam, for example, and I asked you to find S, and you were going to use the appropriate formula, would I expect you to then check your answer by using the poor man's standard deviation? And the answer is no, that would not be part of my expectation, but I'd like you to have an intuitive sense of whether your numbers seem reasonable to you. On a test, sometimes you just get numbers and you fly to the next problem and don't ask, are they reasonable? And that's understandable in a test environment because of the pressure. But if you're doing something and you want to know, is this a reasonable value, I hope you'll recall the poor man's standard deviation to put it in perspective. I think one of the hardest things in the stat course is to get a sense of what standard deviation is telling you. And it's really more related to what we do, and I'll go to the center on this now. What's really more related is the empirical rule we talked about, where if you have a normal distribution, you get that 68, 95, 99.7% of your data within 1, 2, and 3 standard deviations of the mean. So to that extent, I think there's greater meaning. When you look at a bell-shaped curve and you see where the curvature changes and understand that's at 1 standard deviation away, that's another way to determine if you're in the ballpark. So if I can look at a histogram or a stem plot and sketch in a curve, and on the basis of that, look where the curvature is changing, and then extrapolate where I think that is relative to the mean, I can get a pretty good estimate on 1 standard deviation. Now, if I try that with this problem, otherwise we had, again, the 5.6, and so if I were to take time, and let me try it just on a piece of paper here rather than changing to a different board, and I'm going to go ahead and put a 4, 5, and 6, and I have the 6, the 2, the 6, the 9, I have a 5, 7, and a 6, 4. Now, if I look at what I've drawn here, and I look at this stem plot, trying to get a sense of the curve, and let's come off there for just a moment. I'm going to try to sketch in a curve there and explain what I'm referencing. If I look at this associated curve, and I think of the 4 being right here, the 3 being right here, the 5 here, and the 6, and those should be uniform, and I don't have them as uniform as I'd like, then if I think of the curvature changing about in there or about in here, and I drop that down, that is 1 standard deviation from this mean that I have, and the question is, where is this actually centered? Well, it appears to be centered, okay, and again, I'm thinking in terms of a median here rather than a mean with 6 data values. It appears to be between the 6.2 and the 6.6 at a, 5.2 and 5.6, so at about 5.4. So if I think of that center being at 5.4 and this maybe being at 6.5, it appears that eyeballing it, it's about 1.1 for the standard deviation, and that isn't particularly in the ballpark, where I would be trying to represent a value at 0.6. I'm about twice as much as I should. But that's an effort you can do much better with 30 pieces of data than you can 6. 6 pieces of data is a crapshoot. Anything under 5 pieces of data isn't a very reasonable sample size to try to do anything on. But we will find as we go along that sometimes we're stuck with very small data sets. Okay, number 12. As I come off there and go to number 12, it's just a page or so over. And before I go to that, just a comment. This is something that is new in this text. This is on page 53. You'll find me referencing it in a different format, but as we go back to the document cam, the 4-step process. Okay, so the idea of you state the problem, you formulate a solution, you solve and make a conclusion. Folks, this is in essence the 4 steps to a research paper. State the problem. What kind of solution are you going to do? Then go ahead and do the analysis and then provide a summary or conclusion related to it. So if you think in terms of a miniature research project, you spend a lot of time trying to state the problem, something that's worth your time and effort. And you oftentimes go back and look at the literature search to see what other people have done. then you have to choose a statistical analysis that's appropriate to the problem you want. That usually involves getting a data set in some way. Then you do the analysis, and you go ahead. That's called the solve part. And then you talk about your conclusions and what you recommend. Now, whether we call it a four-step process or just common sense to writing up a research problem, you'll find that basic format, whether you're doing a senior project to get your degree, and that is often the case, where you will be in a research project that's supposedly to prepare you for a master's degree, ostensibly which is to prepare you for doctoral work. At which time you try to narrow your focus and get your degree so you can go out and do something substantive once you do have your degree and spend your life pursuing a problem that you may not solve. And that is the irony of it, that you may spend an entire lifetime not finding the solution to something that you were very concerned about. Okay? Think of the just thousands of hours put into research and problems that do not have a solution. Incremental steps, very often very incremental. Well, let's go to the 12th problem. And that 12th problem now is logging in a rainforest. First thing that comes to my mind, if you put an S in front of logging, slogging in a rainforest. If you have ever gone through a rainforest in the rain, it's a mucky kind of thing to do. Well, in this case, we have conservationists, and again, this is a problem that is involved not only in rainforests, this is involved in any forest, the Sierra. Do you go in and clear cut? Now, clear cut, you take everything out. Do you do burning? Do you take out selectively large trees, old growth, leave what's left? There are an enormous number of issues brought here as to how you avoid having massive forest fires that we had, where how many fires did we have during the summer when we had that thunderstorm come through late afternoon, and I believe the figure was in over 2,000 fires. California was burning as a state. And brings up, when that happens, the question of how much effort you put into clearing the undergrowth, the brush, and of course in our area where we have the luxury of Yosemite Valley and the practice the Indians had of burning the underbrush on an annual basis through Yosemite Valley, avoiding that buildup of brush, which ends up in what we call crown fires oftentimes that destroy the trees, not the undergrowth. Well, that's all involved here. And so what we have is researchers take plots of land, and they compared three groups. And what they're doing is asking, if you take one that was logged 1 year earlier, 8 years earlier, and let's see, what do we have? 1 year, 8 years, and that's 3. What is the first group? Never been logged? Okay. So this is virgin forest. And the count we're making is of what? Number of trees for each plot. So if you look at group 1 and look at the data there, is it fairly clear that that's the group with the largest number of trees? And I think it would make sense that if you take 1 year difference, you aren't going to have so many trees, and 8 years later, have you managed to achieve what you had originally? That's more or less the idea. So you're asked, to what extent has logging affected the count of trees? Follow the 4-step process in reporting your work. And so we just referenced that 4-step process. So what could you do based on what you have available to you? Your analysis so far can be descriptive with graphs and numbers. So what would be an appropriate approach here? Because one is not specified for you. You're asked to think about it. What's appropriate? What are your options? I can ask that rhetorically, or I can ask it with the expectation that you would respond. I'm interested in the count of trees. So I'm interested in a numerical value. That would be important. What numerical analysis could we do? What are your choices? means, medians, standard deviations, correct? Okay, I'm not getting any response, so I'll do it as a rhetorical question. It would seem maybe that if you went ahead and calculated the mean for each group, you could look at the means and say one is much larger than the other, which would suggest that perhaps there is a major difference. Now you can eyeball the data and say that group 1 looks like it's going to have what? A rather larger average than the other two. What else could you do of a graphical nature that might give you the same sense?
Stem plots?
Do stem plots or box plots. The stem plot's easier. Run 3 adjacent stem plots. You can't do 3 back-to-back, but you could run 3 adjacent stem plots where your vertical lines line up with the same scale, and then you can determine if there's a shift. That's why the box plot works a little bit better, in which we would have 3 box plots stacked on top of each other, all with the same scale below. Then you look at the mean marker or the median. Now in practice, that is precisely what we're going to do with box plots as we go through the semester. We'll run 3 separate sets of data. Now, this problem anticipates the last chapter we do in the semester called ANOVA, A-N-O-V-A. Chevrolet used to produce a NOVA, and hence ANOVA is Analysis of Variance, which is an acronym, A-N-O-V-A. ANOVA, in which you compare 3 different means simultaneously and ask, is one of them significantly different than the others? Okay, so we're back to the Sesame Street criterion. So there's no one single answer to this problem. And whatever you choose, probably an appropriate analysis could be written. Another one would be histograms. It's just histograms are what? So time consuming. Stem plots much faster. If you do X bar on this, I don't expect you to have to do the documentation where you add all these numbers together. You would just do the formula we had up on the board. X bar equals the summation of X over N. Is that enough for that problem? Okay, number 40. We've got one more to go. Number 40, as we go along, okay, it's not too much further along because I'm running out of chapter. Let's try 62. This is the problem I discussed with you briefly last week, in which I made the comment, you're going to have numbers as we go to the document cam between 0 and 10, whole numbers. Repeats allowed. And you're to choose 4 numbers that have the smallest possible standard deviation, then choose 4 that have the largest possible standard deviation. And the question in part C is whether it is a unique answer. So, if I tell you the answer here, in some ways I destroy the very thing that you were supposed to get out of the problem, which is think your way through it, correct? Now the first part is the easier part, and I don't mind answering that. If all the numbers are the same, then the standard deviation will be 0, because the mean will be the same as the 4 numbers you choose. So if I have all 3s, the mean is 3. So if I take each 3 and subtract the mean, I get 0 in each case. Square 0, I get 0. Add those all up, I get 0. And divide by n minus 1, I still get 0. Is that unique? Can I only do it with all 3s? Well, I can do all 4s, right? All 5s, all 6s. Now the question of how to maximize it. That one, perhaps, if you're having difficulty with it, might be best trying to take the Goldilocks approach. Try 3 different numbers, 3 different sets. One in which you think maybe you maximized it, and then another 2, and see if you get anything more or less for the standard deviation. Now again, I'm disinclined to answer that question exactly because I'd like to look at it from the grading point of view. to see how that went. Well, those are the 4 questions. We've spent the hour answering them. What I've tried to do in covering that, to restate, to rewind a little bit, we talked about box plots and why the problem that involved the box plot should be looked at seriously by you beyond what you did for this homework assignment. Okay? We've also talked about the difficulty with using a stem plot to get the 5-number summary because oftentimes values are rounded. We've looked at the documentation for X bar and S and how that's done. And conceptually, this last problem, dealing with getting a maximum or minimum standard deviation, I think is an important conceptual problem for you to understand what standard deviation is about. Now, I'm going to ask that these problems be turned in because tomorrow I need to focus on Chapter 3 and Lab 3 and get that done in its entirety by the end of the week. So at the end of the 3rd week, we will have done Chapter 3 and we will have discussed Lab 3. So you're going to turn in for me today questions from Chapter 2, the homework questions. Jennifer, as we listen to the